All right, so when it comes to the binomial expansion, he said we're basically starting off with the concept of Pascal's triangle. Now, Pascal's triangle, let's just quickly run through what that is. Pascal's triangle is basically it's a triangle of coefficients. Coefficients. So in particular, let's suppose I want to expand. Let's suppose I want to expand x minus 3, and I expand it to the power of 2, and it becomes x squared minus 6x plus 9. Just for example, in this expansion, we basically have x and minus 3, which are that's where the term binomial comes from. It's the idea of having two terms. That's where bi means two, and nomial means terms, right? So we're dealing with two terms, and that's going to be those two terms. Now, the binomial expansion, initially, we use a plus b, and we expand that, right? A plus b, and we expand that, and we end up with a squared plus 2ab plus b squared. The moment I cube the function, a plus b cubed, and I spend a while obviously multiplying out and expanding the products, I end up with a cubed plus certain other numbers. So you're going to have to be like expanding it. If I have to expand this, a cubed plus 3 a squared b plus 3ab squared plus 1b cubed. And the whole idea behind this is for Pascal's triangle to form, in particular from here onwards, we can see the coefficients. This is coefficient 1, coefficient 1, coefficient 1, coefficient 1. And obviously, if I had a plus b to the power of 1, that's simply going to be a plus b, which is 1 and 1. And if I had a plus b to the power of naught, there was one more level in here. Let's just say I get a plus b to the power of naught. It's simply equal to 1. And what we're noticing is as the power is increasing, we have more and more coefficients. We have more terms. So power of naught gets me only one coefficient. Power of 1 gets me two coefficients. Power of 2 gets me three coefficients. Power of 3 gets me 1, 2, 3, 4 coefficients. And with that, we basically have Pascal's triangle. All right, so that gets us to the concept of what Pascal's triangle is, and Pascal is probably he's the surname of the guy who invented it. So Pascal's triangle, he's the one who sort of, you could say, discovered it. And he starts off with that coefficient 1, 1, and then 1, 2, 1, 1, 2, 1, and then 1, 3, 3, 1. And what he noticed is that if you add up the previous two coefficients, it will just give you the next coefficient, which is weird. That means there's some kind of pattern every time you expand. If I continue to the next one, it's going to end up at 6 over here, and it always has on the outskirts 1. In this case, if I had a plus b to the power of n, then this is going to be n equals to 0, and this is going to be n equals to 1, n equals to 2, n equals to 3. And then when you have to expand something with n to the power of 4, it can be a little bit tedious. Or 5, or 6, or 7, or 16, or 100. It becomes a bit tedious. Another thing you notice is that the powers also decrease. So this is power of 3, and then power of 2, then power of 1, and then over here it's technically a to the power of 0. And b over here is b to the power of 0, for example, b to the power of 1, and it's increasing power of b. So the first term takes on the power of 3, and then suddenly subtract 1, and subtract 1 to get to there. B starts from 0, adds 1, adds 1, adds 1 until it gets there. And that's going to be b to the power of 3. So every single time we do this, there's some kind of way of creating the variables and the powers that the variables have. And this is where the binomial expansion came about. So once they did this, they realized, okay, well, I'm sure there's a pattern. I can use this to create some kind of formula. Let's check if I do use a formula, what will this binomial expansion formula look like? And when they expanded it, they realized, okay, wait a minute. That means I can assign variable powers to each of the terms. When I assign variable powers to each of the terms, the expansion will suddenly take on a certain formula that I can use repetitively overs and overs and overs every time I need to use it. And that's where the binomial expansion concept came about initially. All right. So I have to just quickly get all of this out of the way. If I have a plus b to the power of naught now, I mean n, I need to represent this and these coefficients as well in certain instances. So the coefficients of Pascal's triangle, another thing they noticed was that when you did this, they realized that over here to calculate each of these, you could have used the combination or basically combinations where you have to find NCR. In how many ways can R fit into N? All right, so this binomial theorem based on the coefficients. Now this is the coefficients. What's a coefficient? It's the number in front of each term. The coefficients suddenly took on this value because each of these, this is going to be now when n is 1, right? So this is when n is equal to 0. This is when n is equal to 1. This is when n is equal to 2. And this is when n is equal to 3. And from this, they realize, okay, well, calculating these values over here, for example, let's say 1 to 1. I got 1, 2, and 1. And I've got n in this case is equal to 3, and n is equal to 2 for this one. This becomes 2c naught. This became 2c1, and this became 2c2. And also, if I have to expand this, remember this concept is n factorial divided by r factorial multiplied by n minus r factorial in the denominator, which is why this would be 2 factorial over 0 factorial times by 2 factorial, which comes to 1, 0 factorial being 1, and then 2 factorial over 1 factorial. 1 factorial is 1, so that becomes 2 over 1, which is 2. And this one is 2 factorial over 0 factorial times 2 factorial, which is basically that one there, but the other way around. And it also ends up as 1 with some kind of symmetry. With some kind of symmetry. Okay, it goes up for 2, then it goes back, goes up for 3, then it goes back, goes up for 6, and then it goes back again to 1. And every time you start it off, if you have NC naught, it ends up as 1. And if you have NCN, it also ends up as 1. And that's how the outskirt coefficients always took on the value of 1, because it will have NC naught and NC1 in those spaces. So those coefficients followed that pattern, where we can use combinations to find the coefficients. Now that we have that, you have the binomial expansion of a plus b to the power of n. And this formula is the formula that can be used repetitively. So n c naught a to the power of n plus n c1 a to the power of n minus 1 b to the power of 1, and it continues in that fashion until it gets to ncn b to the power of n. And here you can see n is the power that it takes on, and then you simply minus 1 from each. Something minus 1 from each every single time. But that binomial expansion we can then answer a few questions. For example, we can expand certain concepts or whatever. We can find the first four terms, for example, of an expansion of brackets. Let's say I want to find the first two terms. Let's say find the first three terms. Find the first three terms in the expansion of, let's say you got 3 minus x to the power of 10. So you would apply this here and you say, okay, well, therefore I can see that n is equal to 10. I can see a is equal to 3. And b is actually equal to negative x because it's a positive in the initial formula. I've got a, I've got b, I've got n. I can then put this 4 times out, and that's going to produce the following. It's going to produce 10, in this case 10c naught. 3, remember, takes on, the first term takes on the power, but it'll be 3 to the power of 10. Then the last term takes on the r value, which is going to be 0. We do this expansion 4 times, so 10c1, nc1 can become 10c1, 3, 9 now, negative x1 plus 10c2, 3 to the 8, and negative x to the 2 plus 10c3 3 to the power of, and you notice that this number is those two numbers subtracted. 10 minus 2 is 8, 10 minus 3 is going to get you 7, and then negative x to the power of 3. And also 9 plus 1 is 10, 8 plus 2 is 10, 7 plus 3 is 10, 10 plus 0 is 10. So you know that the powers need to add up to 10. So you just have to get the first one and make sure it adds up to 10. We can then simplify. So I take this to the top here. We can simplify this. 10c naught, remember nc naught and ncn is 1. nc naught is easy to remember. It's equal to ncn. No matter what term it is, or n is, it's going to be 1. And the rest we put in a calculator. So 10c naught is going to be 1 times 3 to the power of 10, which is a huge number, right? So I'm not going to write it over there. So 3 to the power of 10. And then plus 10c1 is 10. Another concept is that if you got 10 nc1, it's going to be equal to n as well. Okay, so it's going to be, in this case, 10 times 3 to the power of 9. Again, 3 to the power of 9, huge number. 3 to the power of 9. The negative will now take over that and make it a positive, bringing x plus 10c2, which we then could put on a calculator and multiply. So I'm going to put on a calculator 10c2, we get 45 for that, times 3 to the power of 8. Now, obviously, I don't have enough space here, but if I had more space, I could write these out fully. It would be really... All right. This is the first 3 terms, though. And what you'll notice is that I'm actually moving in ascending powers of x. What does that mean? I'm going up in powers of x. Why am I going up in ascending powers of x? Because the first term I have x to the power of 0. And then I have x to the power of 1. And then this one's going to be x to the power of 2. And that's going to be x squared over there. Then we got 10c3 times 3 to the power of 7. So that's 120. The dot is basically times 3 to the power of 7. And that becomes negative x cubed. So that'll be x cubed, and that'll change into a negative. Obviously, that's a bit rough, but you could expand it. But that is the answer, and those are the coefficients that we can get for it. Then you get to another question. It's another question where they say that they want you to, without a calculator, find the value of something. In particular, they want you to find the value of some kind of combination. So the question will say, without a calculator, find the value of, let's say, in C3. So when you do this, you take in C3. Remember, the top term is factorial. The bottom term is factorial, but then multiply it by n minus 3 factorial. But this is not simplified, right? So this can go, this is unsimplified. This is just as it is. And by that, you'll see I can, n factorial is basically like 3 factorial, 3 times 2 times 1. 4 times 3 times 2 is times 1 is 4 factorial. 5 times 4 times 3 times 2 times 1 is 5 factorial. So n factorial is simply going to be that number n multiplied by 1 less than itself, then 2 less than itself, and then obviously 3, 4, etc., which means I can rewrite the numerator as that. And because I can rewrite the numerator as that, I can cancel out those two and simplify it. This is a more simplified approach of writing this out over 3 factorial. Okay, a nice way without a calculator to, if you have n, so let's say n is 5, then this becomes 5 times 4 times 3 divided by 3 times 2 times 1. And that will cancel out there. 2 will go into there twice, and then 5 times 2 gets you 10. So you can even simplify it further if it was 5, for example. The next thing they do, using that expansion, they want you to find the coefficient of a particular term. And this is where it gets very interesting. So they'll say, find the coefficient of, let's say, find the coefficient of the expansion of, let's just say I got 1 minus x to the power of n, okay? So they're saying, find the coefficient of the expansion of this in ascending powers, meaning going up, right? Ascending powers of x, all right? Find the coefficient of the x squared term, all right? Find the coefficient of expansion of this coefficient of x squared, or let's make it x to the power of 4 in the expansion of this, for example. Let's give it a value, and you can give this a value. Let's make it, I don't know, 11. Okay. Now, if I have to draw this up, I know that I'm going to take 11 CR. I take the first term, put it in a bracket. That gets raised to the power of 11, and then the second term gets raised to the power of the difference. Okay. Now, if I want to find the coefficient of the power, which is x to the power of 4, that means I need this to become a 4. I need R to become a 5. So therefore, the answer will be 11C5. 1 is still to the power of, no, 1 is going to be to the power of 11 minus 5 is 6, but 1 to the power of anything is 1, right? And then negative x to the power of 11 minus 5 is going to equal 6. And I can't count. That's supposed to be 7, right? 11 minus 7 is going to give 0, 4. Alright, sorry. That's going to be 11 minus 7. So that's 11 minus 7. Because if I put 7 in there, 11 minus 7 will produce the x to the power 4th term, and all I need to do is grab the coefficient from there. That's what we want. We just want the coefficient from there. And that's 11C7. So I put it on the calculator. 11C7 comes to 330. So this is 330. 11C7 is 330. And 1 times anything is 1. Negative to the power of an even number is positive, so that's going to be squared. We get 330 x squared, basically. So what's the answer? 330, basically, is the coefficient of the x. What am I saying squared for? X to the power of 4. So 330 is the coefficient that I'm looking for. Find the coefficient, that will be 330. Now, sometimes it's not so straightforward where you're expanding it like this. It can change, and they can change the question into all kinds of different forms. Like another type of question where they add a bracket to the end of it, and they'll say, obtain the first 3 terms, obtain the first 3 terms in this expansion, right? In the expansion of 2 minus x, let's say 3 plus 3x to the power of 7. Okay, so you're going to find the first 3 terms in this expansion. This is the question. So what you have to do is apply the binomial expansion to this one over here. Okay, so we keep the 2 minus x on the outside for now. And when we apply the expansion on this, remember it's going to be 7c r, but we're going to start with the first 3 terms, right? So 7c naught, and we're going to have 7c1, 7c2, 7c3. This is going to be 3 to the power of 7 and 3x to the power of naught plus, we just keep putting 3 and 3x. We just change the powers. Maybe that's a nice way of remembering. Take the first term and the second term. Let's write it 3 times at least. And let's just see, does it help if we expand it like this? And this is going to be 3c something. We'll click it now. 3x as well. Let's see what happens to this, right? So this is 7. This is going to be 6, 5, 4, and it's going to increase. So another thing we need is to maybe decide if it's in increasing the first 3 terms in the expansion of this. Because x is not in front and 3 at the back, or 3x in front, the first term ends up as a constant, because it'll be 3 to the power of 7 basically. The first term becomes 3 to the power of 7, because this is 1, and that's 1. 1 times 3 to the power of 7 is 3 to the power of 7 anyway. So I just took the first 4 terms. We could continue to more than that if we need to. We better just think about that as well. I'm now going to simplify this, keeping the 2 minus x on the outside. What you can see is I'm increasing, I'm going ascending powers of x, right? This is ascending powers of x from x to the power of naught. This is going to be 3 to the power of 7, the first term. Then it's 7 times 3 to the power of 6. So the 7c1 is 7 times 3 to the power of 6 is 7c1 is 7. 3 to the power of 6 becomes 5,103. Times it by 3 as well. Times it by 3 as well comes to 15,309. 15,309 x. That's this term over here. That term is done. This one here is going to be plus 7c2. This is going to be even bigger. 7c2 times 3 to the power of 5 multiplied by 3 comes to 15,000. And this, by the way, is 6. This is 1. This is squared. Here we go. Times another 3 there. Comes to 45,927 x to the power of 2. And now I'm going to multiply that 2 in. Now if I multiply this 2 in here, I can get the first 3 terms, right? Which means I probably need one more term, which means I have to add one more term in here to get the 4th term, right? But I only need the first 3 terms. So these are my first 3 terms. All I'm going to do is multiply 2 in there. So 2 times each of these will give me my final answer. So 3 to the power of 7 times 2 is 4374. And now we'll be finalizing the question now. This is the last step. Then 15,309 times 2 comes to 30,618. 30,618 x. And the third term will be 45,927 times 2, which comes to 91,854. 91,854 x to the power of 2. And that's going to be that here. So that's going to be my final answer, the first 3 terms, and I've got it all done. Okay, that's the deck start there. The questions can become more complicated in terms. Sometimes they'll ask you for the independent term. So there's some terminology around this. The term that is independent of x. What is the term that is independent of x? That would be this term over here. That term is independent of x. Independent of x. Okay, that means x to the power of 0. Some terminology there. And ascending meaning going up and descending going down. So those are the different things, all built on the concept of the binomial expansion as well.